Good morning. Good morning, everyone. Welcome back. Hope everyone is doing all right. Hope everyone is having a good day. Welcome back to part two of the look and say sequence. I hope you found the last video interesting and hope you managed to find some use out of it. It's a long-standing topic for me that I've had it for quite a while, and I'm glad now that I've managed to explore this in some detail. Before the only interaction I would have had with it was I suppose just reading articles online, and like John Conway and others in the past, getting pen and paper out and drawing it out, which would ultimately come to a stop when I reach a mental block, or at least until I run out of paper. So this is a good way to enact it, get some ideas down in a bit more scale and a bit more detail. So I hope you found this useful. And today I wanted to continue on that and doing a bit more reading. I ended last video with a bit of a question to myself. What did John Conway have at the time when he was working on this? I floated, I think it was Java and a few others. Java wasn't created up until 1995. You couldn't have used that. R as well wasn't around in 1995. C Sharp came in 2000, and what he had was C and MATLAB. C being the precursor to C++ and C Sharp. C++ possibly was around then. I believe that was 1979 or something, but it would have only been in its infancy. C and MATLAB was around in 1970, so he definitely would have had access to that. But he would have had, I suppose, some challenges in terms of scale. Probably wouldn't have been able to build strings. It would have been low level, let's say, analysis that he was able to do. But he would still be able to use it to some effect. So doing further reading, I couldn't find any actual evidence to suggest that he did use either C or MATLAB. Some parts suggest that he would have absolutely known about it at the time when he was doing his research, but I'm curious to see if he actually did use that. That would certainly have helped him out a bit, and I hope he wasn't in his university dormitory simply writing numbers all over the wall, like I probably would have done if I was that invested in this. Anyway, so that's that, and I laid out a bit of the history there. So I wanted to expand on this. So I'm back with the script that we produced earlier. Well, not the same script, because I actually forgot to save the script that we worked on last time. So I'm working on this again. I simply typed this up from scratch a few seconds ago, based on my earlier notes. But I'm going to use this and build this out. So, and here are some of the series values here. So what is it? It's August 12th. Today, August 12th, 2025. It's Tuesday, and I wanted to explore one more property that John Conway found interesting, and that being that if I were to, I'm going to copy this first. If I run this, amongst others, we discussed the exponential constant or the non-constant growth of these digits. The audioactive decay is something we might discover later, but simply looking at the exponentiation here, it's really quite something to marvel. But one of the properties that he noticed, and something you're noticing now, is that the series values are only composed of the digits 1, 2, and 3, and that's it. So if we build on the traditional definition for the look and say sequence, so yeah, 1, 2, and 3 only. There's no 0, there's no 4, and there's nothing else. 1, 2, 3 are really the only digits. We went looking at these series values. It's all well and good simply having a look at these and noticing that that is the case. But like most cases in mathematics and science in general, simply looking at something or a load of possible values is not evidence for such a thesis or evidence for lack thereof. So there has to be a proof, and John Conway did exactly that. He came up with a proof, a rigorous proof, something which I won't go into, but best believe it is out there. So he came up with a proof, but I will settle for an observation today. So if I get another one out, and I'll copy that because I know it's going to keep cycling. What I'm going to do is let's build a table. Let's sort of give credence to that thought that there is no 4, there is no 0, there's no nothing else. So let's keep this. And let's build on this. So what I'm going to do first of all, doing a bit more reading, I realize there is a way to make this a bit more robust. So here last time we used this string and the result. So those together are, let's say, less efficient means when dealing with large numbers, which is not good because the look and say sequence is large numbers. So the result, the string and the result that we see here, they're, let's say, immutable is the word. And what it does, it discards each previous value from memory, which isn't useful because we want to build on these large numbers. So instead we have another means, and that is the string builder. So what that allows us to do, it gives us a bit more efficiency. The string builder is not immutable; it's mutable, whereby it stores all the previous values in memory, and it builds one string where each new value can be built on the value that is saved in memory. Whereas before we were simply creating each new value by again calculating each of the values before it rather inefficiently and rather unnecessarily, when instead we could have had some means where we could have stored it in memory. So that is what this string builder is doing in conjunction with the result append. So this is what we are going to use moving forward. So I need to amend the result output. So results dot append count. Okay. Results dot append input. Dot. Okay. Minus one. So, and then return. What do we want to return? We want to return the result. Dot to string. Okay. So I need something else for this to run. So when we're using string builder, it sort of treats this not as digits, but half digits, half text, which is why we need this new one here. I need a new one using system dot text. Okay, so I believe that's it. And I remember from previous time we did have another package here for the digit output when using the invariant culture. So I'm going to bring that back. Okay, so if I run that, nothing else should happen, but we should still have the digits output. No, the string doesn't contain a definition for length. Yeah, I spelled something wrong. Yeah, length there. And give me a chance to copy it because I don't want this to keep cycling through. Yeah. Okay, so it's done nothing else. I've simply made this more efficient using the string builder. So let's redo that. Okay, so stop that. So what we need to do now, let's build a table. So let's show visually that there's no for involved here. Okay, so what do we need to do? I need to do one last thing because I'm dealing with these digits. I need another static string here. Let me explain what this is. So the string, the format count, and this will. 1 second. Okay. No. Let me write this out first. Okay, so here's where that invariant culture. You saw the string last time that I wrote out. Okay. Okay. Right. So what is this doing? So this int count here, this string count here, it's taking as input all the values of the look and say sequence, and it's simply counting the digits. So every digit that's greater than 0. So we're counting specifically the digits 1, 2, 3, etc., not 0 within the series values. And all this is counting the digits. So it's going to count the ones, it's going to count the twos, etc. And as we keep building in the table, this invariant culture here, you remember from last time, splits every 3 digits by a comma, and we know we're going to need it because these series values grows exponentially. So that's all this is doing. It is simply counting the digits. Now let's build. Now let's create the table. So I don't need. I'm going to copy that in case I lose it. I'm going to start with the string from current 1. So remember that string current 1 indicates that we're starting from the first traditional value, which is 1. Okay, so let's build this out. Let's say these will be the column headers to my table. String, and let's create these headers equals. And so what do I actually want in the output? Let's say I want digit 0 to be recognized. It's digit 0, digit 1. I want digit 2. Yeah, something wrong here. No, I need to. there you go. Digit 1, digit 1, digit 2. Let's come out. Yeah, digit. Pop this out so I don't have to keep on doing that. Digit 3. Digit 4, should one exist, which it doesn't apparently. And then other digits, all other digits will fall under this category here. Great. Right, so let's put a bit of daylight between you and that. So those are the headers, and let's give it a column width. Column width would equal I don't know 16. That should be enough to accommodate for these large digits. So now we want a means by which the outputs can be outputted, digits to be outputted. Let's call this to be outputted. Okay, so what will this be? So we want each of these columns to be separated by a pipe, like that. Yep. So what we want to do for each string, I'll explain this. Let me write this out. Each string, each headers. Okay, so let me write this out. Console write h dot pad left column width. Close that, close that. Yeah. Am I missing something? I don't think so. Yeah, so console dot write and split with a pipe. Good. Yep. What have I done? So this console write, or I suppose yeah. So we're splitting every column by the pipe, and so for each of the h's here. First of all, what are we doing here? This H align pad is a bit intuitive. It says pad line left, but what it's doing is aligning everything to the right and separating each of the values with a pipe. Okay, so what the H is actually doing, the H in the header, let me describe this. H is simply each of the header, and it's recognizing these are each of the H's. The H is saying for each of the H, which is the 0 or the 1, etc., or for everything that falls under these, we want to align everything to the left, and we want to be able to output everything underneath it with the digits. So that's not the full story yet. All this is merely outputting the table format. We haven't found a means to output the actual digit count. So this is what this next part is going to be. So while true. Okay, so let's think a bit. So while true, I'm going to need another one there. Okay, so this is going to be a bit of a long one, so bear with me. Counts equals new integer count, 10. So all we're doing here is we're counting all the digits from 0 to 10, or 0 to 9, I suppose, exclusive of the 10. Going down, so this part here, this will be the part that actually counts the occurrence of each digit, counts the occurrence of each digit. Okay, so I'm going to use that notation again for character C in current, and the character C is basically the digit. The character C will be recognized as the 0, as the 1, 2, 3, 4, etc., 5 in all these cases. C is the digit that we're counting in each of the series values. Okay, so C character, so what am I doing here? Is the digit equal to C? So is the digit equal to 0? Is the digit equal to 1, etc.? If so, we need to count it. So it counts C minus 0. C minus, oops, I need it's not an apostrophe, is it? I think yeah, apostrophe negative. Okay, and we simply want to keep on counting that as long as there is something to count. So going back here, that would be here. This will be counting, let's say, this long string of digits, the 1, 1, 1. And we're going to keep on counting that until it hits something that's not equal to 1. Great. So moving on, we want to be able to print all of that. So what is this doing? So print the digits with the alignment. Print digits with alignment. Okay. So console.write. So across each pipe, each digits or each field separated by the pipe. I hope this actually works. I couldn't find a way where we couldn't write sections of this to make it run. We had to write it all out, all in one go. So int I is equal to 1. So this is where we sort of separate the 0 to 4, which is kind of what we care about, versus all the other digits, which we don't quite care about. So 0, 4, I plus plus. So remember, we only care about 0 to 4 here, and then all other digits. So that's why we're writing this one loop for the 0 to 4, and we're going to do exactly the same for all other digits. Okay, so what do we want? We want the console to write within the table, format count, counts I for each series, each digit within the series value. So again, we're left aligning it. I've written quite a bit here. I'm not even sure if this will run. No doubt there's a spelling mistake or some other error around here. Okay, so console.write. Okay. Okay, so end that. So this part here will simply output all the digits from 0 to 4, and it'll have them aligned under each of these digits here, or the field headings for the digit. So we need to do the exact same for all other digits. So other digits starting from 0, but running from, or a count starting from 0. Okay, for integers, I is equal to 5s, and these would be the all other digits. 9, I plus plus. Okay, others. These would be the others. Okay, so plus equals counts I. Okay, so we're almost done here. And so all we need to do, again, is now print the actual table now that we've done this in conjunction with the actual digit count. So let's do that. Console format count others dot left column width. Okay, and then console dot right. So separating everything by the pipe again. Doesn't have to be the pipe, it could be anything else. Console.write line. So, and we're moving everything down after or we're creating a new line every time we output a digit for each series value. And so now we need to add back the get this part here, which you remember, it stores in memory the next term. So after we've reduced the next term, that next term would become the current term. Okay, so I'm going to not add threading here. I think this is. I'm going to give this a once over here. 1 second to make sure I have done this right, which I probably haven't done all in one go. So bear with me. There should be a caps letter there. Format spelt incorrectly there. So I think, yeah, I'm missing a semicolon there, and I've spelt format incorrectly again. Okay, so let's see, does this actually run? Yeah, let's let it run. Perfect, look at that. Somehow I've got a misalignment there. Why is that? I'll leave that for now because that's fine. I'm having a bit of a problem here. I've tried to scroll down a bit and it's lagging a bit. It's lagging my scrolling. So again, we're still dealing with the large numbers here, but I think we are running into a problem a bit. So I'm going to pause this. I'm going to let it finish. I'm going to come back. Otherwise, I'll risk this computer crashing. Let me come back. Great. So I've given this 5 minutes to run now. So I'm going to see. This should be done if I collapse the font a bit and use the touchpad to make this a bit bigger. So here we go. You can see under the digit 4 count, all other digits, 0 as well. There is absolutely no occurrence of the digit 4 in the look and say sequence. And so this goes all the way down until the session simply ends at the bottom. But that is fascinating. We don't get any digit 4s. So I'll keep this here. I don't want us to run this again, but I'm hoping we can do something a bit different here. Actually, no, I'll just explain that. Look at this. So what is this? 437 million digits of 1, 282.5 million digits of 2, 162 million digits of the digit 3. So these are exorbitant amounts of digits on their own. So how do we even quantify? What does this look like? So if I can entertain an analogy here, let's say for a brief moment that the Earth was made of paper. bear with me. The Earth is made of paper, the oceans are made of paper, and it's all is one big, long, continuous, navigable stretch of land. What this looks like, if you add those three numbers there, the 437.5 million, etc., you get 882,752,750 digits. So, what does that number even look like? So I'm getting a bit of paper out here. So if I were to write any string of numbers, if I were to write, let's say the number 437,527, etc., and let's say I'm not going to write out, actually no, not the comma separators, but if I was to write this number out here, any number, my typical handwriting would allow for 4 millimeters of space, 4 millimeter length width for each digit, a space between each digit of 1 millimeter. That gives 5 millimeters per single digit. So 5 millimeters times this 882 million figure gives 4 million. Sorry, it's a long number. 4,413,763, which is about 4,413 kilometers, or 4,500 kilometers. So, thanks to the great Eratosthenes of Cyrene, not to be confused with Aristophanes of Wellington Street in Covent Garden. Note the spelling. So Eratosthenes was the one who gifted us with the fact of the Earth's circumference is 40,075 kilometers. So which means at a digit count of 4,413 kilometers of this, the largest series value that we can output, if we were to start at the North Pole, if we were to travel down the prime meridian, the meridian line, that means we would have passed the level of Iceland, we would have passed the level of the Faroe Islands, we would have passed the level of Oslo, Norway. We would have near enough surpassed London. We'd have passed Greenwich, we would have passed London. And so that's about the distance. If you were to write all these digits out from the North Pole all the way down the meridian line, you wouldn't make it to the equator, you wouldn't make it to the South Pole, you would near enough make it to London. So let's sort of quantify this a bit more and doing a bit of more reading about this. If you were to start at the Shetland Islands in the United Kingdom, travelling down, you would have passed Portugal, you would have passed Morocco, and you would end up somewhere in the Western Sahara. If you were in Moscow and you wrote these numbers heading eastwards to the Vostok, you would end up somewhere in Mongolia, or near enough around the regions of Mongolia. If you were at the Hushan eastern terminus of the Great Wall of China, and if you followed the wall heading west, you would have passed Beijing, Zhaoyuan, and you would end up somewhere in Xinjiang. So further on, if you were in Miami, and if you headed in the northwestern direction, you would have passed Georgia, you would have passed Tennessee, past Missouri, past Colorado, past Montana, past Wyoming, then Montana. Sorry, you would have arrived in Seattle. You could see the Space Needle, and you would have even been able to make it up to Canada. Finally, if for all my friends in Malta out there, if you were to start on the very outer perimeter, or the navigable part of the perimeter in Malta, then you'd be able to circle the island of Malta 22.43 times. That's the walkable coastline. It's about 196 kilometers, so circa 22 times that you can write these digits around the island of Malta. So that's how large these numbers are. That's the sort of scale that John Conway was dealing with, and this is what we deal with now. So when I say there is no digit 4 or anything else, that's not entirely true. I said there is something we can do, and if we go back to this string count here, I said the look and say sequence typically starts with 1, conventionally. Emphasis on the word typically. If I change that number there to 4, then I'm sure we might see some digit 4, maybe 1 as we keep going down, and that would be about it. So there we go, we get the 1 digit there, and everything else seems still in line. We still exponentiate rather wildly. But there it is, that digit 4 only appears once. What else can I? What if I made that 4 lot to the digit 4? Okay, 4 lot to the digit. Oops, it's not going to let me do that easily. 4, because it's still running. 4, 4, 4. Yeah, okay. I would probably get two digits of the 4. There we go. There's the 2 digits of 4. But then remember, we get 4 lots of the digit 4, then we get 2 lots of the digit 4, and then we get 2 lots of the digit 4, and then ultimately that one digit collapses into 1 4. So why exactly do we not get 4 in the traditional sequence, and why does 4 simply vanish? Well, ask John Conway that, but it seems, remember, the look and say sequence, it's made up of two numbers. There's the digit itself and there's the counting number. So those together, the string doesn't seem to allow itself to get long enough to account for anything longer than a string of digits longer than 3. So what happens here? So that's pretty much it. I mean, John Conway had a very, very rigorous proof of that. Something which I might come back to, might read in my own time. What else? What if I put 5s, a load of 5s in there? It's not letting me do that. I know it's willing. Good. So 5. Yeah, there we go. We'll get the 4 and the 5 there. The 5 falls onto the other digits. There you go. It's simply going to keep going there. It's slowing down as I get on. And finally, I won't keep going with this. I think you get the point. One last one. What is it? Let's say 10. What about the 0 here? 10. Yeah. So bear in mind, there's no digit 10. The 10 will fall under the digits 1 and 0. So there you go. We get our digit 0. We get 1 0 there. Oops, I can't do that. And then the 1 from the 10 is simply absorbed under the digit 1. So that's it. I won't go any more into this, but this really is an interesting topic. There is more arithmetic in there, and I'd find that book that John Conway wrote. I believe it was a book detailing his thesis on the look and say sequence. But that is fascinating. That's an interesting topic. So anyway, that's it. Hope you enjoyed this. What happened up there? Why am I getting a split line there? Maybe it's a semicolon. Maybe it's a console right line. Anyway, thank you so much. Let me know your thoughts on this. Hopefully this is useful for you, and if it's nostalgic for you, hopefully so. Let me know in the comments below what you thought. Any criticisms, comments, any thoughts at all are greatly appreciated. It helps me also as I move forward in these videos for you. So no, thank you so much. It's August 12th today, 2025, Tuesday. I'll get this video out shortly. And thank you so much. So I will be I'm going to be out next week. Have a few things to sort out. So I don't think I'll be posting a video next week, but I will get back to a video with another topic, which I don't know what that is yet. I'm sure I'll find one in the week after. I believe there'll be August 19, so that'll be the week of August 25th, that is. So I'll see you around August 25th. Thank you very much, and see you soon. Have a good day, everyone.